Hi, Assalamualaikum warahmatullahi wabarakatuh to our lecturer, Dr. A.K.M. Zaki Hussein. This is a presentation for electromagnetics induction in renewable energy system. Okay, the slides and the report is prepared by NUREIN AFIEFAH BINTI Muhammad ZAKI. Matrix number B122310540. Next is Muhammad KHAIKAL bin KAMALUDIN B122310583. And next is Muhammad IZZUDDIN bin Abdul Rahim B122310525. And lastly, LUQMAAN bin ZULKIFLI B122310015.
Let's begin with the core idea behind this study. The growing global demands for clean energy has driven innovation in renewable technology, especially wind and hydroelectric systems. This research aligns with Sustainable Development Goal 7, which promotes affordable and reliable energy for all. At the heart of the system is a fascinating mechanism. Mechanical energy from natural source is converted into electrical energy through variation in magnetic flux. This not only enhances our energy infrastructure but also add a unique appeal to how we present and understanding sustainable solution. To guide this exploration, we have outlined three key objectives. First, we aim to understand the core theory of electromagnetic induction and its mathematical foundation. Second, we apply Faraday and Lenz's law, especially within the context of renewable energy system. And finally, we will analyze how this principle operate in real-world application, like wind turbine and hydroelectric generator. This objective ensure a strong theoretical base and practical relevance. Now, let's dive into the core theory, Faraday law of induction. This principle states that an electromotive force, or we call EMF, is induced in a closed loop when the magnetic flux through that loop change. Mathematically, is expressed as EMF equal the negative rate of change of magnetic flux over time. This change can occur due to variation in the magnetic field, movement of the conductor, or can be both. Faraday law is fundamental because it's underpin how mechanical energy is transformed into electrical energy in modern electromechanical system.
Hi, Assalamualaikum warahmatullahi wabarakatuh. Next, we will go to Lenz's law and Maxwell equation. First, when we start establishing the theoretical foundation with Lenz's law and Maxwell equation, the Lenz's law is actually an essential physical manifestation of principle of conservation energy. It states that the direction of the induced current will always create a magnetic field that opposes the initial change in flux, which explain the mechanical resistance we see in generators 2 alongside that we rely on the Maxwell-Faraday equation, which is the curl operator times electric field equals to minus the changes of magnetic flux over the changes of time, which is the differentiation of P over differentiation of T. And as for the engineering application, this equation is critical for this application because it allows us to optimize the geometry of pose and state of a rotor in generator to ensure the maximum efficiency. Next, we move to motional EMF and Lorentz force. This concept defines how we actually generate power from motion, specifically using the Lorentz force equation, which is as stated as a definition produced by motion of a conductor through a static magnetic field common in wind turbine. That's for the example. The Lorentz force equation is force equal to electrical charge in bracket electrical field plus conductor speed with times with the magnetic flux. In application like as a common wind turbine, which the rotation of the wind turbine blades V interacts with the magnetic flux density of B to drive the electron flows. So understanding this interaction is vital for our design utility, as applying this knowledge leads to the creation of the more efficient energy harvester capable of operating under various environmental conditions.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syamil IZZUDDIN bin Abdul Rahim. My matric number is B122310525 and my part is application. So let's begin by looking at one of the most visible application of Faraday's law, which is wind turbines generator. In this system, the process starts mechanically. The kinetic energy of the wind rotates the turbine's blades, which are connected to a shaft that spins a rotor inside the main generator. This way, the physics of induction comes alive. As the magnet on the rotor spin, they create a time-varying magnetic flux that cut across the stationary inducting coil known as the stator. According to the Faraday's law, this continued changes flux that induce an electromotive force, which is EMF. So the result is production of alternating current electricity, which effectively convert the mechanical energy of the wind directly into electrical power. Next, moving on hydroelectric power plant, we see a similar principle applied on a much more massive scale. Here, flowing water provide the immense mechanical energy required to drive large turbine. Because these systems are so large, to maximize this, the generator utilizes a ferromagnetic cores. These cores are essential because they enhance the flux leakage, thereby increasing the efficiency of the induced voltage. However, generating the power only have the battle. This is where the transformers come in. The transformer also rely on Faraday's law to step up the voltage. By increasing the voltage, we can transmit the power over a long distance through the national grid with minimal loss, ensuring the energy reach the consumer efficiently. Finally, we look at the future of this technology, which is smart drawing and wireless transfer. We are now moving beyond traditional generator into a realm of inductive coupling. This technology explores transferring power between coil without any direct contact, using magnetic resonance. This particularly revolutionary of a smart green ecosystem is allowed to integrate of wireless charging for electric vehicle, making green transportation more seamless. By integrating this induction principle into modern infrastructure, we are not just generating power, we are building a sustainable network that reduces our global reliance on fossil fuel. This evolution is simple generation to smart distribution smart to next chapter in electromagnetic application. So that's all for me. Thank you.
Next, we go to methodology, analysis, and modeling. The first is analytical approach. By applying integral form of Faraday law to calculate voltage based on system geometry and frequency, we are using the software like COMSOL Multiphysics and ANSYS Maxwell for finite element modeling of FEM. The simulation helps predict flux distribution and account for non-idealities like material saturation. We must address the real-world efficiency challenge in energy conversion that exists despite our theoretical frameworks. There are several factors that reduce efficiency, starting with resistive heating, where the energy is dissipated as heat within the conductors.
Now that we look at the methodology, let's see how the data support the theory. For the validation, our study confirmed that the design we just discussed worked exactly as Faraday predicted. We found that the induced EMF is directly proportional to both the number of coil turns and the strength of the magnetic field. This validates the mathematical formula we've been using. Next, for the core finding, essentially, we have proven that Faraday's law isn't just a classroom theory. It is a robust and verifiable foundation for harvesting energy from natural resources. Lastly, physical observations. We also clearly observe Lenz's law in practice. Whenever there was a flux change, we measure mechanical resistance in the generator. This is the physical proof of the induced current opposing the change that created it. Moving on from result and discussion, let's go to efficiency challenge and energy compensation. Despite theoretical in the real world, we don't get 100% efficiency. There are several factors that cause our result to deviate from the ideal theoretical framework. The first is resistive heating. As current flow through the coil, some energy is inevitable loss as heat. We also have to deal with magnetic loss, specifically eddy current and hysteresis within the metal core, which drain power from the system. In more advanced setup, high frequency issue like the skin effect make it even harder for the current to flow efficiently. To overcome this, we can't just rely on the basic theory. We must advance material and better physical design to minimize this loss. Looking ahead, how can we use what we learn to improve the system? So let's move to future recommendation. Advanced material. First, we need to prioritize research into new material that reduce those magnetic and heat loss we just mentioned. This is the fastest way to boost generator efficiency. Technological innovation. We should also look beyond turbines and start applying this induction principle to things like wireless charging for electric vehicles and smarter power grids. Refined modeling. Instead of simple math, we recommend using high-resolution simulation to predict exactly how magnetic field will behave in complex machinery. Finally, we go for the sustainable design. We should focus on making this induction-based system lighter and more portable so we can harvest energy in more places than ever before. In conclusion, Faraday law remains the absolute operational backbone for modern power distribution and our global transition to clean energy. This fundamental principle has catalyzed the shift into the electrified era and continue to meet the rising demand for sustainable power. By integrating this law into Maxwell's equation, induction has achieved a universal status that allows engineers to precisely control and predict energy conservation. Ultimately, while efficiency challenges exist, Faraday's discovery remains a timeless and essential tool for achieving a sustainable, low-carbon future and meeting our goal for affordable, modern energy for all. Thank you.